In this episode, we are stepping into one of the most serious kinds of software risk because it helps explain how a weakness in an application can turn into direct control over the system running it. Remote code execution, RCE, is the idea that an attacker can cause a target system to run commands or code that the attacker supplied or influenced, even though that attacker is not physically present at the machine. For a brand new learner, that matters because this is not just about reading data, changing one setting, or causing a minor error on a screen. When RCE is possible, the attacker may be able to make the server or device behave as though it is carrying out the attacker's instructions, which can quickly lead to theft, disruption, persistence, and deeper compromise. That is why this topic matters so much for CySA Plus students and future analysts. It sits at the point where weak application design, unsafe input handling, system privilege, and business impact all come together in a very direct and very dangerous way. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. At a basic level, RCE happens when a system takes outside input and ends up treating some part of it as something to execute rather than something to store, display, or process safely as ordinary data. The attacker is not just sending a bad value that causes a harmless glitch. Instead, the attacker is trying to influence the application so deeply that the application or server performs actions under the attacker's direction. You can think of it like convincing a receptionist not just to pass along a message, but to hand over a master key and start following a stranger's instructions inside the building. The core issue is that the system loses control over the boundary between untrusted input and trusted execution. That loss of control is why RCE is so dangerous. Once a machine starts running attacker-controlled instructions, the problem is no longer limited to one screen, one field, or one feature. The weakness can expand into a much broader compromise depending on what the system can access and what privileges it has. One reason beginners find this topic intimidating is that it sounds as though the attacker must be using extremely advanced techniques every time. In reality, the severity comes from the outcome, not always from the complexity of the path used to reach it. Sometimes RCE follows a chain of smaller weaknesses that together create an execution path. In other cases, one badly exposed feature gives the attacker a direct opportunity to influence behavior in a way the designer never intended. The system may be parsing uploaded content, processing a request, handling a template, interacting with a scripting feature, or passing information to a lower-level component in an unsafe way. The exact method can vary a great deal, but the essential risk stays the same. The attacker has moved beyond influencing what the application shows and into influencing what the application or server actually does. That is why analysts care so much about RCE. It marks a shift from misuse of a feature into potential control of the underlying environment. To understand why this threat matters so much, it helps to distinguish it from other kinds of vulnerabilities. Some weaknesses allow information disclosure, meaning the attacker can read something that should have remained private. Other weaknesses allow unauthorized modification, where data or settings can be changed. Some flaws disrupt availability and cause a service to crash or stop responding. RCE can sometimes include all of those consequences and more, because once arbitrary instructions are executed, the attacker may choose what goal to pursue next. They might read sensitive files, create new accounts, install malicious software, move laterally, disable monitoring, or use the compromised system to attack other resources. This is why RCE is often seen as one of the most severe categories of application and system risk. It gives the attacker flexibility, and flexibility is dangerous because it means the incident can evolve in multiple harmful directions based on the value of the compromised asset and the creativity of the person exploiting it. Many real-world software features can become dangerous if they cross the line between handling input and executing behavior without strong controls. An application might accept content uploads and process them in the background. A web service might pass user-supplied data into a script or interpreter, A management platform might include automation features meant for administrators, but expose them too broadly or validate them too weakly. A backend process might transform data, unpack files, render templates, or call system-level functions in ways that assume the incoming content is safe. None of those features are automatically reckless, because modern software often needs dynamic behavior to be useful. The problem appears when the application trusts the structure, content, or origin of input more than it should and allows that input to shape execution in a privileged environment. That is one of the key lessons for beginners. RCE is rarely about the idea of flexibility itself being bad. It is about flexibility becoming execution power without strong enough boundaries around who can influence it and how. The word remote is important here because it tells you the attacker does not need local physical access to the machine at the moment of exploitation. The attacker may be across the internet, in another office, or already sitting elsewhere inside the network after gaining an earlier foothold. If they can reach the vulnerable service or persuade it to process attacker-controlled content, distance becomes less important than the trust relationship between the input and the system. This is what makes remote threats especially serious in connected environments. A weakness that allows execution from a reachable interface can expose an organization to compromise without the attacker ever touching a keyboard attached to the target machine. In enterprise settings, that can affect public-facing applications, internal management tools, remote access services, cloud workloads, and specialized business platforms. Analysts therefore need to think carefully about exposure. A vulnerable process on an isolated lab device is one thing. A vulnerable process exposed to the internet or to a broad internal population can be a completely different level of organizational risk. Another key factor is privilege, because the damage caused by RCE depends heavily on what level of authority the compromised process already has. If the affected application runs with limited permissions, the attacker may still do harm, but the immediate blast radius could be smaller. If the application runs with broad administrative rights, access to sensitive files, connection to internal databases, or the ability to communicate with many other systems, the consequences can become much more severe very quickly. This is where a basic security principle becomes extremely practical. Least privilege matters because it helps contain the damage when something goes wrong. A flawed application is bad enough. A flawed application that also runs with excessive power turns one mistake into a far larger incident. For a beginner, this is a useful way to think about the relationship between vulnerabilities and architecture. The same RCE issue can look very different in two environments depending on service account rights, segmentation, data access, and whether the compromise process is surrounded by strong boundaries or almost none at all. It is also important to understand that RCE rarely appears out of nowhere as an isolated magic trick. More often, it reflects deeper problems in how software treats untrusted input, how it invokes other components, and how much freedom it gives certain features. Unsafe deserialization, command injection, template misuse, exposed administrative automation, insecure plugin behavior, and vulnerable third-party libraries can all contribute to paths that eventually end in code execution. Beginners do not need to memorize every technical subclass to grasp the bigger lesson. The real pattern is that the system allows data from an untrusted source to shape execution in a context that holds more trust than the source deserves. Once you see that pattern, the topic becomes less about scary jargon and more about clear defensive thinking. Ask whether the application is evaluating, running, expanding, or passing along input in a way that could turn user influence into system action. That question alone helps explain why so many different technical paths can still belong to the same RCE family. A common misconception is that successful RCE always results in a dramatic visible failure, such as a crashing application or a system taken offline immediately. In reality, skilled attackers often prefer the opposite. They may use execution quietly, with minimal disruption, because a live and stable compromised server is more useful than a broken one. A machine that keeps serving customers while secretly leaking secrets, running hidden tools, or connecting to internal systems can do far more long-term damage than one that fails loudly. This is why defenders cannot rely only on obvious outage signals when thinking about execution threats. Sometimes the system continues to function normally from the user's perspective while the attacker is already exploring the environment, establishing persistence, or collecting credentials. Analysts should remember that quiet compromise is often more dangerous than noisy compromise because it gives the attacker time. The absence of visible chaos does not mean the absence of execution. It may simply mean the attacker is being careful because the compromised asset is too valuable to waste on short-term disruption. Once an attacker gains execution, the next phase often matters more than the first one. The initial exploit may only provide a narrow foothold, but from there the attacker may attempt privilege escalation, credential theft, persistence, lateral movement, or tampering with logs and security tools. This is why our CE should be understood not only as a vulnerability category, but as a launch point for broader compromise. A web application server with execution access might reveal database credentials. Those credentials might unlock more records or other services. A compromised internal management system might already have trust relationships with endpoints across the organization. An attacker who starts with execution on one host may end up affecting many more systems because the environment around the compromised process was too trusting or too interconnected. For a CySA Plus learner, this is one of the most valuable insights. Security analysis is not about staring at the first flaw in isolation. It is about seeing how that flaw interacts with the rest of the environment and how quickly one executed process can become the first move in a much larger attack story. Detection can be difficult because our CE does not always create a neat alert that says attacker code ran here. Security teams may instead notice strange process creation, unusual child processes launched by an application, outbound traffic patterns that do not fit the system's role, sudden access to files the application normally would not touch, or the appearance of new scheduled tasks, scripts, or accounts. Application logs may contain odd requests or malformed content that preceded the event, while endpoint monitoring may show suspicious execution paths afterward. In cloud environments, abnormal use of workload credentials or unusual calls to internal services may be part of the story as well. The challenge is that visibility must span more than one layer. Analysts often need application context, process telemetry, network behavior, authentication activity, and file changes to understand whether a suspicious action was merely an error or a true execution event. That is why mature detection is layered. No single log source tells the whole story, especially when the attacker tries to keep execution quiet and short-lived. From a vulnerability management point of view, our CE findings usually deserve serious attention because the potential impact is so broad. Still, good analysis should go beyond the label alone. Analysts should ask whether the vulnerable function is exposed externally, what privileges the affected service holds, whether authentication or segmentation reduces reachability, how easy exploitation appears to be, and what business systems the host can touch after compromise. A theoretical RCE condition in a limited internal tool is still important, but it may not carry the same urgency as an execution flaw in an internet-facing platform tied to sensitive customer data or core operational workflows. Context matters, yet our CE almost always deserves respect because even a narrow foothold can become dangerous in a permissive environment. This is a good example of how technical severity and business reality need to be connected. The right question is not only could code run, but also where could it run, under whose authority, and what doors would open once that happened. Prevention begins with the idea that untrusted input should never be allowed to shape execution without extremely strong control. Safer design choices include limiting dynamic behavior, isolating high-risk processing, validating inputs carefully, removing unnecessary interpreters and administrative features, applying secure update practices, and choosing architectures that reduce the privileges of exposed services. Network segmentation and workload isolation matter because they shrink the consequences when a failure occurs. Strong account management matters because the credentials available to the compromised process influence how far the attacker can move. Monitoring matters because even the best design cannot guarantee perfection forever. For a beginner, it is helpful to think of prevention as building layers that make execution harder to reach and less rewarding if it happens anyway. A disciplined environment assumes that some application weakness may eventually appear, so it tries to ensure that one exploited process cannot effortlessly become total control over the business. Response planning also becomes critical because the discovery of possible RCE should change how defenders think about urgency. If an organization has reason to believe code execution was achieved, the issue cannot be treated like a routine cosmetic defect waiting for the next maintenance window without deeper thought. There may already be persistence, credential exposure, data access, or tampering that extends well beyond the original vulnerable feature. Responders may need to isolate the host, examine related systems, rotate secrets, review logs for follow-on activity, and determine whether the application was used as a stepping stone into more sensitive parts of the environment. This is why our CE is as much an incident concern as a development concern. Even when the initial report arrives through scanning or testing rather than through a confirmed breach, the organization should think carefully about what exploitation would mean in practical operational terms. Analysts add real value when they help leaders understand that potential execution is not merely a software flaw, but a possible pathway to larger business compromise. By the end of this discussion, remote code execution should feel less like a mysterious expert-only term and more like a clear warning about what happens when a system loses control over the boundary between input and execution. The attacker is no longer limited to asking the application for information or nudging it into a minor error. Instead, the attacker may be able to direct the system to perform actions on their behalf, which can open the door to data theft, service disruption, hidden persistence, and wider compromise across connected resources. That is why our CE remains one of the most serious categories of weakness for analysts to understand. It combines application design, privilege, architecture, visibility, and business impact into one threat pattern that defenders cannot afford to dismiss. Once you recognize that the real danger is not just bad input, but attacker-influenced execution inside a trusted environment, you have the foundation needed to analyze these threats more clearly and to understand why preventing them is one of the most important goals in modern cybersecurity.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.